of machine learning models. Okay, I'm going to take example from one of my paper, which I have recently wrote on high entropy alloy design. Okay, so the concepts which we are going to discuss today, these concepts can be useful in any kind of machine learning modeling. Means how we can use machine learning models further. Okay, so we have discussed a lot about that, how to develop better machine learning model. But now in today's class, we are going to see how we can use those machine learning models. Okay, so today's class is quite important for those who are working with design of high entropy alloy, for those who are working with design of perovskite, or any other machine learning model based project they are working on. So in today's class, they can get the insight that how this machine learning model can be further utilized for data intensive uh, problems. Okay, so some problems we are going to solve today, that is large scale prediction by using machine learning model. Another problem that we are going to see today, that is how we can optimize the process. The machine learning model which you have constructed, that machine learning model can be used as objective function in any optimization problem. Okay, so I'm going to give this example in terms of alloy design. Okay, so let's see what is done in this paper. So I will just, we have seen this paper earlier as well, I guess, but at that time you didn't have that kind of maturity to understand. But I'm sure that now you have been through a lot of coding and all, so you can understand what is happening. Okay, so if we just look at it, what I have done here is that I have generated some models for high entropy alloy. I used molecular dynamic simulations over here. So with the help of molecular dynamic simulations and random sampling. Okay, so the concentration of individual element that we can see over here. So that is what the whole high entropy alloy is composed of. There is some concentration of aluminium, nickel, chromium, ferrous, cobalt. Okay, so like this, what I gathered some 128 samples of high entropy alloy, different configurations of high entropy alloy. Okay, then I conducted molecular dynamic simulations for those configurations and gathered Young's modulus and density. As you can see here, I have some concentration of aluminium, cobalt, chromium, and nickel, and ferrous, and corresponding responses I have gathered from the simulations. Okay, so stiffness is there and density is there. Now, if you just look at the constraint over here, is that first constraint is that compositional summation should be 100. Okay, for each individual sample, you will see the composition sums up to be 100. Okay, so that is one constraint. Another constraint is that the individual concentration, okay, the individual concentration must vary within 5 to 35%. Okay, so each individual elemental concentration, what we are seeing over here, these are varying in between 5 to 35% of the concentration. So we have two constraints over here. Number one, the elemental constraints, that each individual element concentration must be within 5 to 35. Another is summation constraint, that all the concentrations must be sum up to 100. Okay, so these we are going to utilize. How we are going to utilize, we will see. Okay, so let's look at the flow diagram, what I have done here. So first thing is that randomly sample compositional space for this high entropy alloy and constructed 128 samples. Okay, so in these 128 sample spaces, individual element variation is in between 5 to 35%, and summation of all the concentration sums up to be 100. So that was the constraint I utilized while generating random samples. Okay, next I conducted molecular dynamics simulations for uniaxial tensile deformation. Okay, and gathered the responses corresponding to each sample, as you can see over here. Right. Next step, with the help of, now I have the input features and I have the corresponding responses, target values, right? So now I can construct a machine learning model. So what I did, I use after one out of 128 samples, I used 108 for training, and I kept 20 samples out of the fold for validating my model. Okay. Next, once the model is constructed, I use this model for large scale predictions. So what was the large scale prediction for? Influence of individual parametric variation. What happens if individual parameter is varying? Okay. So if I have these five features, if individually aluminum is varying, what will happen to the stiffness and density? If individually chromium is varying, what will happen to the stiffness and density? Okay, that I wanted to know. Second, the sensitivity analysis. So out of this information, I get to know that variation in which element will have more impact on the responses. Okay, so that's why sensitivity analysis was conducted. Then multi-objective optimization was done by these GPR models were utilized as objective function in an optimization problem. Okay, so the optimization problem was unique over here because we have contradictory objectives. Contradictory objective means that we have stiffness and density. So we want to maximize stiffness and minimize density. Okay. So this was the whole work which was conducted in this work in this paper. Okay. So let's go through. So these were the hyperparameter search range and selected hyperparameters for individual models, as you can see. So this is the first based on the data itself. So data which we have got, based on that, how individual element or individual feature is correlating with the response that we can get out of this. So as we can see from the color bar, it varies from -1 to 1. So -1 corresponds to blue and 1 corresponds to red. So what we can see from here is that aluminum concentration, if we just vary aluminum, we are having negative influence on the Young's modulus, means stiffness, and negative influence on the density as well. So what we can observe from here, if aluminum will increase, stiffness of the alloy has to increase, will be decreasing, and density will be decreasing. Whereas if we just look at the nickel concentration, we have somewhat positive influence on the stiffness and density. So if nickel increases, concentration for nickel increases, the responses are bound to increase. Okay, so that's what information we can get from this correlation analysis, that how individual feature is having correlation with the responses. And also we can have a look that how individual feature is having correlation with the individual feature. Now if we would just want to see how aluminum, or I would say the chromium is correlating with ferrous. Okay, so if chromium increases, ferrous has to decrease, means ferrous will decrease. That's what our data is suggesting. Okay, so what data in initial data is suggesting, that's what we are getting out of this. So far no machine learning is involved. I'm just interpreting what data is giving us. Okay, that is first task for you. Whenever you are working with machine learning model, just check how your input data, the data which you are going to utilize, it is giving you some information. Okay, next is, now I will use the data for model construction. As you can see, I have taken scatter plots, right? So 108 training data and 20 validation data, that is shown over here. Corresponding error, percentage error, is shown with this plot, right? Same thing I have applied to density as well, as you can see. Okay. So now once the machine learning model is constructed, this validation data we have not used while training the model. Okay. So with the help of this validation data itself, what we can observe that there is sufficient accuracy. We can get high fidelity predictions out of this model. Okay. So now once that is established, now we can use this model for further investigation, right? So what I did for in further investigation, as you can see in these plots, here I have shown two different kinds of sample spaces, right? The first one, the number one, which is written. So in this, what is happening? The ferrous is varying in between 5 to 35%. Okay, so these blue points are corresponding to training data. These red points are corresponding to validation data, which we kept out of the fold. But there is second set of samples. These are 10,000 samples. Means gather randomly sampled 10,000 points in between 5 to 35% for individual feature here. Okay, so ferrous is varying in between 5 to 35 samples, like that we have 10,000 random samples. Same is for nickel also, same is for cobalt also, same is for chromium also, and same is for aluminum also. Okay, so now if we club all this together, we will get this kind of sample space, right? We will get this kind of sample space, which will be 10,000 samples, okay, in total. But the constraint has to remain same, that individual sample is varying in individual feature is varying in between 5 to 35%. At the same time, the summation of all the features must be 100 for one instance. Okay, so this constraint has to be followed for this prediction data as well. Okay, so now since I have a better model which can predict for any point in between 5 to 35% of the variation of individual feature, so I can deploy that model for the getting prediction for this second sample set, which I have gathered. This is 10,000 samples. So now just imagine if I wanted to conduct simulations for these 10,000 samples. So for me, one simulation takes around 24 hours or 27 hours, sometimes 36 hours as well. But if I wanted to do the simulations for 10,000 samples, you can imagine how much time intensive it would be. Okay. So for such kind of problems where the time intensiveness, resource intensiveness is there, we tend to utilize the computational efficiency of machine learning model. Okay, that's the beauty of machine learning model, is that we will construct the model by having some small number, relatively very small number of samples. The model we will assess for better accuracy. If model with the model we are getting better accuracy, we can deploy those models for prediction for some higher number of samples, as you can see here. Okay, so now once these samples are there, what I did, I wanted to know what happens if only one feature is varying. Let's suppose I'm talking about aluminium. If aluminium alone is varying and rest all the samples are at their mean value. Okay, mean value means 5 plus 35 by 2. Okay, that means 20 20 20, like that. Okay, so if aluminium is varying and rest all we are taking, or else we will take it rest all as equiatomic, because whatever the percentage of aluminium will be, and aluminium is varying from 5 to 35%. So let's suppose if aluminium is 5, so rest of the features must be 95. So each individual feature will be 95 by 4. So like this, if aluminium is 35, that means 65. Summation of all the other features will be 65, and individual feature will be 65 by 5 by 4. Okay, you got it. So this is how we are varying individual features. So now when aluminium is varying in between 5 to 35%, what is happening to the Young's modulus? Okay, so this is what we are getting from for 10,000 samples. I have 10,000 samples here where I am just varying aluminium, rest of the samples are equiatomic. Okay, what is happening to the Young's modulus? It is decreasing. What is happening to the density? It is decreasing, right? Whereas in nickel, what we are seeing with the variation in nickel, we are having positive, means increase in the Young's modulus, increase in the density. Now, if we just look at the initial data, what it was telling us, with the increase of aluminium, the Young's modulus and density has to decrease. With the increase in nickel, the stiffness or Young's modulus and density has to increase, right? The same trends we were getting from our initial data. And after implementing machine learning model, the same trends we are getting, right? So this is how we fortify that, okay, the model which we have got, it is giving us same trends which we should get, okay, which our earlier data is showing. So that's how we also establish that model is working fine. Okay. So I hope this is clear so far. If there are any queries up to this, you can just go ahead and ask. Then we will move on to next section. Just think of this in your terms of your project, okay, and ask questions based on your project. What kind of project, means how these things can be implemented in your project. Just think in that fashion. Then you will get some questions, I guess.
Excuse me, sir. Like in that graph we drawn with 1,000 samples now, sir. For that R
Mm-hmm.
sample space, I didn't get that part actually, sir. Like what we are doing, like what's the
Okay,
graph about, sir?
this one.
Yes, sir.
Okay, so what I'm showing here is that how many samples I have used for training the data, how many samples I have used for prediction. I'm sorry, validating the model, and how many samples I have used for prediction. So what is happening here is if I just look at this 108 samples, okay, so all the blue samples which you are seeing over here, so these corresponds to individual variation in the features, right? This corresponds to ferrous, this corresponds to nickel, this corresponds to cobalt, this corresponds to chromium, and this corresponds to aluminium. That's what it is projected here also. If we just look at it, if I just want to project this part alone, okay, if I just want to project this part alone by some scatter plot, okay, so here, as you can see, it is varying in between 5 to 35, right? So same thing I have projected in a different sense over here, that it is varying in 5 to 35. So training data is varying in between 5 to 35. Validation data, I have selected some random 20 points in between, as you can see, right? But when I want to deploy this model, right, I want to use this model. So I will use this model for large scale samples. Those large scale samples are 10,000 samples, which I randomly generated in between the parametric range of variation, right? The range of variation is not changing here. It is 5 to 35, 5 to 35 for individually. So that's how I'm projecting that what kind of data set I'm using for training, testing, and prediction. Did you got it now?
Yes, sir. I got it. Thanks, sir.
Okay. Okay. So are there any other queries so far? Okay. So let's move on to the next part then. So far what we have seen, first of all, we have constructed the model. Okay. I'm sorry. First of all, we have seen that how our initial data is telling us something. Then we have used that data for construction of the model. We have constructed the model. Then we have deployed the model for large scale predictions. These predictions are based on 10,000 random samples which were generated within the parametric range of variation. Okay. Next step, how we can use this model further. Okay. So I have told you about sensitivity analysis, right? So these predictions which we are getting here, these we are using for sensitivity analysis. Okay. So what we are doing here, individually one feature is varying, all the other features are kept equiatomic, as we have seen. And then we have seen that what is the effect of individual parametric variation on the responses. So with the aluminium, we can see the responses are going down. With the nickel, we have seen that responses are going up. Chromium, again, responses are going up. Okay, ferrous responses are going up. So cobalt, we have got some mixed kind of thing for Young's modulus. First, it is going down, then going up. Okay, so this is what we have got for 10,000 samples. Now, how can we use this information for performing sensitivity analysis? So for that, what we did, we used coefficient of variation. Okay, so coefficient of variation is called sensitivity index. Okay, so when we have, how do we calculate that? We got the standard deviation of the responses. So at this stage, we got standard deviation of stiffness. Okay, and what is the mean value of stiffness? Okay, so standard deviation by mean, that will give you the variation, coefficient of variation corresponding to aluminium. Same thing we conducted for nickel. Standard deviation of stiffness divided by mean of stiffness. That will give us coefficient of variation for nickel. Same way we have calculated coefficient of variation for chromium, standard deviation of stiffness divided by mean of stiffness. Okay, so like this, we have got 5 coefficient of variations for aluminium, nickel, chromium, ferrous, and cobalt. Okay, then we add those up. Okay, and we divided individual coefficient of variation by that. So I have shown this here, as you can see. So relative coefficient of variation is coefficient of variation of individual feature divided by summation of all the coefficient of variation. and coefficient of variation can be calculated for as standard deviation for that particular feature and mean value of response for that particular feature. Okay, so that's how we get this kind of bar plot. Okay, so this kind of bar plot for stiffness or Young's modulus and for density. So what we are observing here is that variation in aluminium is having very high influence on the stiffness, right? That's what is shown with this sensitivity index as well. Okay, then variation in nickel is also having effect. So followed by variation in nickel, followed by chromium, followed by ferrous, and followed by cobalt. So this gives us idea that what will happen if one individual parametric variation will take place. If aluminium is varying a lot, we can expect very huge variation in the stiffness. That's what we are getting out of this. Okay. Similarly, if nickel will vary, there will be some. So what is the nature of that variation that we don't know here? Okay, means whether it is going to increase or decrease, that we have already established in the previous graphs, that it is going to increase for nickel, it is going to decrease for aluminium, but from the looks of it we cannot tell whether it is going to increase or decrease. So for this, from this we can only get the information that what will happen, means how one input feature is influencing our response. Okay, so from here what we can get, that aluminium, nickel, chromium, so chronologically we can see the variation is minimizing. So cobalt and ferrous doesn't have much influence on the stiffness. So variation in these features will not have much influence. Okay. Similarly, for density, we can see the aluminium is having huge influence on the density, followed by nickel, followed by cobalt. Okay. So here chromium and ferrous doesn't have much say on the density. So variation in chromium and ferrous, we cannot expect much difference in the density. Okay, so from this we get some common ground. If we are to maximize this y and minimize this rho, ferrous is that point where we don't need to make much changes, right? Because ferrous is not influencing either of the responses. Okay, so that's what we get out of this data driven sensitivity analysis. Now once this is we got, we can use the model for multi-objective optimization. Okay, so multi-objective optimization, I have used genetic algorithm over here, and in this genetic algorithm based multi-objective optimization, I got this kind of Pareto solution. Okay, so just look at these red points and see what is happening. So on the x-axis we have Young's modulus, on the y-axis we have density. If we just move uh, left side on the x-axis, the Young's modulus is increasing. Okay, if we move downwards on the y-axis, the density is decreasing. So we need decreased density and increased Young's modulus. Okay, but at this stage of we will see that density is high, Young's modulus is high. At this stage, density is low, Young's modulus is low. So we have to stay in between somewhere, right? So the samples corresponding to these, the number 2 is written. These samples can be of our interest where we are getting sufficiently high Young's modulus with sufficiently low density. Okay, so like this we can get, when we have contradictory responses, we can use multi-objective optimization. Okay, so this is what this paper tells you, and I have validated it with the help of some simulations. Okay, so this is one more thing which you can explore. Okay, so this is very good thing because so far the machine learning models were considered as a black box models. Okay, we cannot interpret how machine learning models are working. But with the help of explainability given by SHAP parameters, you can just write it down, note it down. Those who are working with the machine learning based projects, they can use this in their work. Okay, so that idea for demonstrating all this is that you can get some ideas that how you can implement these things in your project. Okay, so SHAP based explainability gives you some idea that what features are contributing high in your prediction making. Okay, so if we just look at the SHAP parameters, so SHAP parameters means the SHAP value which I'm showing over here on the x-axis corresponding to first model, that is GPR underscore y. So negative Sharpe values is given on this side, positive Sharpe value is given on this side. Okay. So what we can observe here is high and low is given like this. So this red portion corresponds to high value of aluminum concentration. Blue portion corresponds to lower value of aluminum concentration. If we just look at this only. Okay. So what we can interpret here is that lower value of aluminum concentration. Okay. Lower value of aluminum concentration. Since our objective was to increase Y, right? Maximize Y. So lower value of aluminum concentration is having positive Sharpe value, means it is having positive influence on the Y. Whereas higher value of aluminum concentration is having negative Sharpe value. That means it is having negative influence on the response Y. Okay. Same interpretation can be obtained for nickel as well. Higher value of nickel concentration is having positive influence on the Y. Lower value of nickel concentration is having negative influence on Y. Okay. Same interpretation can be done for the density as well from these plots. Okay. So like this, you can interpret the Sharpe summary plots. These are the summary plots, I guess. Yeah, Sharpe summary plots. Okay. Now, this force plot over here in the C, it tells you that if you are, we have got some solutions here, right? Let's suppose we have got some solution. We have got some solutions in this region. Okay. And we want to make prediction for this region, and we want to see what are the different features which are influencing the prediction in this region, because this is the region of our interest. We would like to have the samples from this region because this will have some sufficiently high Young's modulus at the relatively lower density, right? So now if I just want to make prediction for any of the samples in between, and I want to check what is each input feature is contributing, how each input feature is contributing, that can be checked through this force plot. Okay. So now I'm interested in Young's modulus of 80.12. Okay. So for this, how each individual input feature is varying. Okay. So what I can see, cobalt is not having any say because I cannot see cobalt here, right? Whereas aluminium, nickel, chromium, and ferrous, all these things are having some positive influence, higher influence, I would say, when we want to have Young's modulus of this value. If we just look at the aluminium side, aluminium is quite large. So it is having far higher. Nickel is little bit small. Okay. The region for nickel. The region for chromium and ferrous is not that much. The negative influence that is having of cobalt, that is not at all shown in the, because if you want this Young's modulus, these are the different values which we have to take. Okay. Same way, if we want to have this density, you can see how much each input feature is influencing. So aluminium must be this much. Okay. For the same concentration, we have taken the density as well. So as you can see that if we want to have this density, how each individual parameter is going to play. Okay. So I hope this is clear to you. This is how the Sharpe values are varying for individual model that is shown here. So with this, the discussion on this paper is ended. I just want to know if there are any queries, please go ahead and ask. I can explain the plots once again so that you will get the understanding.
Sir, can you
Are there?
explain the Sharpe part again? So like how it's used or like why it's used? Sir?
Okay, so Sharpe is actually the. Uh, I will just give you one example. If you have a team, right, and that team is playing some game. Okay, so now if that game is to be won, the contribution of each individual player of the team has to be taken into picture, right? If you want to just predict whether the team is going to win or not, right? So similarly, Sharpe analysis, it is actually based on game theory, where individual feature is considered as a player in a game, and while prediction, it is assessed that how individual feature is making difference in the prediction. Okay. So for that, what is given that some SHAP values are assigned to individual predictions. And based on those SHAP values, we get the information that how individual feature is going to affect. So as I told you, if you just look at the summary plot, there is high values of the feature is given by red in color and low values are given in blue in color. Okay. So now if we just want to have a look at aluminium alone, consider aluminium is one feature or one player in this whole game, right? So now if aluminium is high means red in color, we are getting negative SHAP values. That means it is going to negatively influence our response Y over here. Okay. When aluminium is low means blue in color, it is having positive SHAP value. That means if low aluminium is there, we can expect increase in Y. That's what we were getting from our previous data driven approach as well. And that is fortified by SHAP explainability also. Okay, so these steps are performed to ensure whether whatever we are saying that is true or not. This is kind of a evidence we are providing that whatever we have interpreted from the model, that is accurate. Okay, so that is why we perform different kind of studies to get to the same decision or same interpretation of the data. Okay, same way for the SHAP interpretation over here also you will find that aluminium higher values of aluminium causes negative influence on the row, lower values of aluminium causes positive influence on the row. Okay, so this is how you can interpret the summary plots. Now if we want to pinpoint the prediction, that how the prediction is happening, what are the features one particular prediction. So one particular prediction, let's suppose in this plot which I have shown, I am just going with the Young's modulus, that is 80.12, and corresponding, so 80.12 it would be somewhere here, and corresponding density would be 7 point something, right? So I want to see that how machine learning model is predicting this. Okay, so for that I will use this force plot. For one individual prediction, I will use the force plot. So the predictions were 80.12 and 7.25. So how individual features are influencing this? Means what are the different features? So aluminum is having very high positive concentration, right? So 14.96 is the aluminum concentration. Nickel concentration is 24.78. Chromium concentration is 80.25 and ferrous concentration is 21.82. Okay. Same is evident over here also. So cobalt is 18.39. But this higher and lower, this actually tells you that what is happening. What is happening is aluminium, nickel, chromium, and ferrous is having higher influence on the Young's modulus, whereas cobalt is not having much influence. Okay. So this is how you get the interpretation that how individual feature is affecting your model. Why that is necessary? Let's suppose I am going to deploy this model in some industry, right? So I should know what parameters I have to vary and how much I have to vary. So if I just look at this, I will tell that, okay, cobalt variation in cobalt cannot influence the model much. So we can vary cobalt, but we cannot vary aluminium much, right? We cannot vary nickel much if we are just going to fix our outcome. Okay, so you got it how this SHAP actually tells you the information, Gohan?
Yes, sir, I got it now. Thanks. Thanks a lot.
Okay. Okay, anyone else? Any query? You all are working with the machine learning based projects. I would encourage you to ask some questions, clear your doubts. Just think of it in your how you are going to implement this in your projects. That's how you will get the information that what kind of questions you can ask. Shall we move on? Okay. All right. So now we have seen this. Let's see how we can implement this same thing in Colab. Okay. So I will just give you some hints, some ideas that what can be done. So first of all, we will discuss that one, if we have only one response, like most of you are working with single response also. So in that case, what you can do, okay? So I have this data set. So I have this data set where I have just considered stiffness, right? This data set I have shared with you as well. Okay. So we are just going to look at this data first. Okay. So now, first of all, the same thing we are doing. We are constructing the Gaussian process regression. Okay. Importing the data into the Colab framework, segregating X and Y. So by this part, you have already known what is happening. I'm just using some customized kernel over here with some constant kernel value, pattern, and white kernel. So this kernel looks something like this over here. Okay, 1 raised 2 into pattern, length scale 1, new is given 3 by 2. So like this. Okay, so this kernel is known as pattern 3 by 2. You might have heard or you might have explored. Okay, so I will use this kernel for model construction. I'm getting fairly good model predictive accuracy over here for train and test both. Mean square error, if I can see, it is quite low. Scatter response is also good. Okay, so now once this part is over, with this we have established this model is working fine, and we can deploy this model for any kind of sample space where individual parameter is varying in a stipulated range. Okay, so now we can use this model for further analysis. Okay, so inverse design of alloy. Inverse design of alloy means that we have some essence of the outcome. So that essence is that we want to maximize stiffness. Okay, so here I'm going to utilize scipy.optimize. So from scipy.optimize, I'm importing minimize. Okay, I'm defining the constraint. What was the constraint? If you recall, summation of all the input features must be 100. Okay, so I'm just looking for the feature settings for which this summation is okay, 100. Okay, otherwise it will be removed. So this sum constraint is the function which I am defining. I'm defining the objective function. What is the objective function? I have some input space. This input space is taken from the here. Okay, so this is the input feature space for me. Okay, and I want to use model. The constructed model is model 1. The name of the model was model 1. So I'm going to use the same model over here. Okay, negation of model dot predict. So negation tells that I want to maximize stiffness. Okay, so whenever you want to maximize the response, this negation will come. When you want to minimize the response, this negation you can remove. Now I want to store some objective values and concentration values. Objective values means the stiffness values with each iteration, and what is the concentration of individual input features for those iterations that I want to store in this objective values and concentration values. Next, I want to define a function callback. Okay, this callback actually gives you the iterative approach. Okay, so this objective value is negation of objective function. This objective function we have defined here, right? So negation of this objective function. Negation is again used for maximize stiffness. Okay, so from func tools, I'm importing partial. So now this particular portion is where I'm going to implement the optimization process. Okay, so this partial is utilized over here. I'm taking objective function and model into account. So objective function is the function which I have defined here. Model we already have defined earlier. Okay, so this is the initial guess where all the input features are at 20, 20, 20, and 20. Okay, bounds I have defined for individual input feature, that is 5 to 35, 5 to 35, 5 to 35, like this. Okay. Yeah, I will share the paper, Gautam. No problem. That is not yet published yet. that is under process, but I will share it. Okay, so 5 to 35, 5 to 35, like that I have defined the bounds. Next, the constraints. There was a constraint that is type equality, right? So we want to sum all 200. That was the constraint, and I'm taking this function sum constraint. This function I have already defined here. So I'm taking this function over here. Okay. This callback is again for making this process an iterative process. Okay. So when I run this, it will give me something. Okay. So now I want to check what are the optimal solution and what is the maximum stiffness I am getting out of this. So optimal solution is 535. So aluminium must be 5, nickel must be 35. Okay. Other features like ferrous, cobalt, chromium, I guess. Aluminium, nickel, chromium, ferrous, cobalt. So this is aluminium, nickel, ferrous, chromium, cobalt. Okay. So if you want to plot that what is happening iteratively. So at first iteration or zeroth iteration, it was 70, the stiffness. And as you can see, the stiffness is increasing iteratively, right? And with this increase in stiffness, what is the corresponding concentration that we can see over here? Okay. So concentration 1 is for aluminium, concentration 2 is for nickel, and so on. As you can see that it is varying. Okay. So at last we are getting some convergence. As you can see in concentration 1, concentration 2, concentration 3, concentration 4, and concentration 5. So at 12th iteration, you will find that these are the converged concentration of individual uh, features. Okay. So that's how you implement your machine learning model. Here what I did, I used the machine learning model, the generalization capability of machine learning model to perform the optimization process. Okay. Is this clear? Yeah, Mohit Madhav, do you have any query? Are you speaking? I am not able to hear you. Okay. Okay. Is there any doubt? Just let me know so that if there is, I can explain the code once again, or else I will move on to the next code. So I hope this is clear. I will share the code with you. You can explore this on your own as well. Okay. So those who are working with the data set which Kalavani madam has shared or Anjana ma'am has shared. So that data you can utilize over here for this kind of okay analysis. Okay. So what changes would be there that you don't have the equality constraint in Kalavani ma'am's data or Anjana ma'am's data. There is no uh, constraint given, right? There is no equality constraint. So you can remove this constraint part. You don't have constraint, and you can explore that how the same thing you can perform without the extent and without the constraints given. Okay. So this is for the first part where only one response is there, and we want to maximize that response. Let's move on to the next part where we have a data set with two different responses like this. Okay, so I'm taking only 80 samples with me. I'm not able to locate where I have kept all the 128 samples. So I found this. I'm going to utilize this only. Okay. Okay, so let's work this out. So first step is same. We are going to construct two different machine learning models here. Okay, so that is the crucial step. You should ensure that your machine learning model is working properly. Okay, so I think I'm not going to use the scikit optimize, but okay. So all the dependencies are there. So again, I'm going to use Gaussian process regression, the kernel functions which I'm going to use. Okay, so base or CV, I think I'm not going to use here. Oh, yeah, I'm going to use it for hyperparameter tuning. No problem. Okay, so now I will just take copy path. Okay. So this is my data set. Again, I will get the feel of the data, that how my data set looks like. Okay, so same thing, aluminium, cobalt, as we have seen earlier, right? One more thing we can observe is that rho and E, these are all having positive correlation.
Sir,
Yes, Golaram?
is that like a confusion matrix?
No, this is called correlation matrix, not confusion
Okay, sir.
matrix. This is called
Okay.
correlation matrix. So we have conducted Pearson's correlation. We want to see that how much linearity individual individual feature is having with the response. So this negation shows that it is negatively correlated, and this positive shows that positively correlation. Okay.
Okay, sir. Okay, sir. Thank you, sir.
Okay. So here what we can see that rho and E are also positively correlated with each other. If we just look at the density and Young's modulus 0.9, that is positive value. So if Young's modulus is increasing, density is increasing. If density is increasing, Young's modulus is increasing. This we have already also seen in the plot, Pareto plot, which I have shown in the final stage. This one, right? So at increased Young's modulus, we have increased density. At reduced Young's modulus, we have reduced density. Okay, so that's what we are getting from our input data. All right. So now again, we will segregate X, Y1 and Y2. I'm separating X train 1, X train 2. So X train 1, X test 1, Y train 1, Y test 1 for Y1. That is for Young's modulus. And train 2, test 2, these are for density. Using this kernel for Young's modulus, using this kernel for. So now, as you can see in constant, I have made the changes. So if I am just using one over here instead of, or else I'm just putting it. But if I use one over here, we will see that how the model is not working well for this. So I just want you to understand that this constant value, this is also one hyperparameter which you can play with. So now if I just use kernel one means this kernel again for the GP2, that is second model, you will see the model is not working fine. So base search is utilized for finding the hyperparameters based on this hyperparameter search. I think it is going to take time. So this is base search 2 for second model. GP2 I'm taking here. Parameter space is same. Number of iteration is 20. And cross validation folds are 5. So I want you to understand that I'm using the same kernel here, the kernel which I have defined here. I'm using the same kernel for both the models for now. And we will see that what we are getting. Okay, so we got the best hyperparameters for the first model, second model. Now let's evaluate. Okay, so prediction from the first model, prediction for the from the second model, R square corresponding to the first model, R square corresponding to the second model. Okay, it is working fine, I guess. So mean square error for the first model, mean square error for the second model, right? Let's make the scatter plot. So this is for stiffness and this is for density. Okay. Percentage error for the first response, percentage error for the second response. So I'm taking train and test for percentage error. Plot the. So his plots is showing very low percentage error in both the cases. Right. So now I'm going to use these models, the constructed models for multi-objective genetic algorithm optimization. I'm using non-dominated sorting genetic algorithm optimization over here, and that is taken from deep package. Okay, so first of all, I will install this deep package. From deep package, I'm going to import base creator tools algorithms. So I will define the objective function. So this is the objective function evaluate. I'm taking aluminium, chromium, cobalt, chromium, ferrous, and nickel as the individual features. So y1 predict takes best model 1. So this best model 1 corresponds to best model we got for Young's modulus, and best model 2 is the best model we got corresponding to density. So y1 predict and y2 predict are the two responses, and as you can see, negation is there for y2 here. We want to minimize it. Okay. So next we are giving the constraint. The constraint, as you know, the summation of all should be 100. Okay. The parametric ranges are for individual features 5 to 35. Okay. We are using deep toolbox. In this deep toolbox, what is the evaluate function? So what is that function? We have already defined that evaluate function here. So we are taking that evaluate function in this toolbox dot register. Okay. So we are getting some minimum value, maximum value in the parametric range by using this function, by using this for loop. These are some inbuilt values which we want to provide. Okay. So fitness, this is multi-objective problem. So fitness multi is the task. We are assigning weights for individual response. So we are giving positive weight for the stiffness since we want to maximize that. We are giving negative weight to the density since we want to minimize that. Okay. Again, we are taking individual, how that individual has to vary. So there will be an array based on numpy. Okay. All right. So again, the individual, we have 5 different individuals over here, and this individual will vary and repeat. Okay. So there are certain values I would like you to explore on your own. Just explore this particular portion. So now there are some certain features, certain parameters associated with genetic algorithm. That is population size. I'm going with 100. Crossover probability. I'm going with 80%. Mutation probability. I'm going with 20%. Number of generation is. We will discuss all these things in coming classes. But for now, I just want to demonstrate that how you can use this deep package for NSGA multi-objective optimization. Now you will get this, but the problem, there is some problem. I'm getting some fitness value over here. I'm getting the Pareto as well, but there is some problem with this code. The problem is that I'm getting negative value for the aluminium. The summation must be 100 for all 5, but I'm getting somewhat negations. So I think there is some problem with the code. So I'm giving this code to you. You just explore this, and I will be giving the data set as well. So there is some problem with this code where negation of the input feature is coming. That should not be there. Just explore this on your own and try to incorporate something so that this particular problem is resolved. Okay. So I just want to show you that this is kind of plot which we get for the Pareto front. So what we are observing here, the maximum stiffness is in this region, right? And minimum density is in this region. Okay. So there is some problem in my original work. I used MATLAB. This is something I done very recently. So I'm still figuring out where the problem is. But still, I just wanted to demonstrate you that deep is the package that you can utilize for multi-objective optimization. Okay. So is there any doubt so far? We have covered that how machine learning models can be enhanced, the predictive accuracy can be enhanced by using hyperparameter tuning. Okay, so once we have that model, what we can do with the model, that I have shown in today's class. So I hope this is clear that what you can perform with the help of your machine learning models. And I'm open for discussion. If any of you have any doubt or query, please, now is the time you can ask. So I'm expecting some response. How was the session? Did you understood anything?
Yes, sir, we have understood.
Okay, that's good. What about others? Okay, great. So I will be sharing all this with you. You can just explore this on your own. And if you face any difficulty at any point, so I'm also working on this NSGA part. Once this is done, I will share the revised code with you. Or else you can also go along that and find the problem where the problem is. Okay, so I will be sharing the data as well along with the code. Okay, so do we have Kalevini madam? Kalevini madam, are you available?
Yes, sir. Yes, sir.
Okay, so you can go ahead with the attendance.
I'll take attendance. Section A, say your attendance. Number 1.
One present, ma'am.
Okay.